Welcome to the course UEC001. In this module, we will discuss few numericals on operation amplifier. So let us discuss example. Let us discuss example. If R1 equals to 100 kilo ohm, Rf equals to 500 kilo ohm, what output voltage will receive if input voltage is 2 volts? Given that A part op amp is working in inverting mode, B part op amp is working in the non-inverting mode. So let us find the solution of this problem. I think problem is very simple. One can easily understand. For the better presentation, I am preparing the circuit diagram first. So inverting configuration is given, series resistance and feedback resistances have been given. So in the first step, let us deal with part A. So 2 volt input is given. I have used here. Series resistance is given as 100 kilo ohm. I have applied 500 kilo ohm. I have used. This is my inverting, non-inverting terminal. Supply voltage VC and minus VC. We have to find this output voltage V. So you can recall, for inverting amplifier, output voltage V0 divided by input voltage Vin, which is equals to minus Rf upon R1. So with this relation, I can easily calculate output voltage V0, and this will be equals to minus times of Rf upon R1 multiplied by input voltage Vin. So put all these values. Minus Rf is given as 500k divided by R1 is given as 100k multiplied by input voltage is given as 2. So k is cancelled. K means 10 raised to power 3. So as available in both numerator as well as denominator, so I have taken k, cancelled, and it will be now minus 5 multiplied by 2. So it is minus 10 volts. That means my output voltage V0 equals to minus 10 volts for inverting amplifier. So output voltage is minus 10 volt for inverting amplifier. So first case is solved. Let us move to the second case. B part of the circuit, and in this B part, let us draw the circuit first. Now I will be a bit faster. Over here, inverting terminal is grounded, 2 volt signal applied to the non-inverting terminal, feedback resistance is connected here, measuring output voltage V0 in this situation. Suppose plus Vc and minus Vc. Values are given as 100 kilo ohm, 500 kilo ohm. So for non-inverting amplifier, this is non-inverting amplifier as input is given to the non-inverting terminal. So for non-inverting amplifier case, voltage gain, closed loop voltage gain AV equals to V naught divided by V in ratio of output to the input. This will be equals to 1 plus RF on R. As we have to find the value of output voltage, so this will be equals to 1 plus RF upon R1 multiplied by input voltage V in. So put the values, it is 1 plus 500 into 10 raised to power 3 divided by 100 into 10 raised to power 3. Now I have represented in terms of ohms multiplied by input voltage is 2 volts. So this cancel out and these two zeros will also be cancelled out. V naught will be equals to 1 plus 5 multiplied by 2. So V naught will be equals to 12 volts. Interesting point is this. In case of inverting amplifier, my output voltage was minus 10 volt. There will be 180-degree phase shift between input and output. You can see from this relation. And for non-inverting amplifier, there is a slight variation in the voltage. We notice 12 volt instead of 10, but there will be no phase shift between input and output. So depending upon the application, one can choose either inverting configuration or non-inverting configuration. So I hope with this example, you are in a position to understand the concept of inverting and non-inverting amplifier. If RF equals to 1 mega ohm, if RF equals to 1 mega ohm and summing amplifier is given, summing amplifier circuit is given, determine the output, determine the output voltage. Now again there are two parts. So in part A, V1 equals to 1 volt, V2 equals to 2 volt, V3 equals to 3 volt, R1 equals to 500 kilo ohm, R2 equals to 1 mega ohm, R3 equals to also 1 mega ohm. In part B, V1 is given as minus 2 volt, V2 is given as 3 volt, V3 is given as 1 volt, resistances are given as R1 equals to 200 kilo ohm, R2 equals to 500 kilo ohm, R3 equals to 1 mega ohm. So let's see the solution. For better understanding, I am preparing the circuit first so that idea will be clear. Now here are three inputs. So I am just considering the three input case, all connected to inverting terminal, feedback resistance RF, connecting non-inverting terminal to ground. For simplification, I am marking V1, V2, V3 so that same circuit can be used for both resistance R1, R2, R3, and this is RF. And this is my summing amplifier. This is my summing amplifier circuit. So if you can recall the formula which we have discussed, the output voltage of summing amplifier is minus feedback resistance RF times V1 upon R1 plus V2 upon R2 plus V3 upon R3. There is a slight change in the notations as we have used voltages V1, V2, V3 and resistance R1, R2, R3. Now for the first case, directly put the value V naught equals to minus 1 into 10 raised to power 6 because resistance is given in mega ohms. V1 is 1, so it is 1 divided by R1 is 500 kilo ohm. So 500 into 10 raised to power 3 plus this is given as 2 divided by 1 into 10 raised to power 6 plus 3 divided by 1 into 10 raised to power 6. By solving, now it will have 10 raised to power 5 and 5. So I will take multiply numerator and denominator by 10. So it will be 10 divided by 5 into 10 raised to power 6. That means uh, V naught will be equals to minus 1 into 10 raised to power 6. So I am making powers common. So it will be 10 divided by 5 into 10 raised to power 6 plus 2 divided by 1 into 10 raised to power 6 plus 3 divided by 1 into 10 raised to power 6. So now I can check this particular term 10 raised to power 6 will be cancelled out from numerator and denominator. Okay, and now we will have output V naught equals to minus times of 10 divided by 5. So it is 2 plus 2 plus 3. So it is minus 7. That means for the first case, my result is V naught equals to minus 7 volts. V naught equals to minus 7 volt. So this is the first case. Similarly, you can find the second case also, and I'm keeping this as a homework to you. Okay, I'm just putting the answer for the case B. For the case B, the value of output voltage V naught will be equals to 3 volts that you have to verify. So it is very simple. You can use the formula, put all these values and try to solve. Example number 4, the statement is for an operational amplifier, for an op amp, value of slew rate is given. Value of slew rate is given. It is given as 2 volts per microsecond. This is the value, and you have to determine what is the maximum, what is the maximum closed loop, what is the maximum closed loop voltage gain that can be used, that can be used when input signal varies by input signal varies by 0.5 volts in 10 microseconds. So this is very interesting numerical. I'm reading again so that you can understand what is the given data and what is the requirement. So in an operation amplifier, slew rate is given 2 volts per microsecond, and it has to ask what is the value of maximum closed loop voltage gain. That means we have to determine the value of AVD. We have to find this value that can be used when input signal varies. Variation of input signal is given by 0.45 volt when there is a variation in time of 10 microsecond. The solution. So let us see the solution. If you can recall, we have studied that closed loop voltage gain AVD equals to what? Output voltage upon input voltage. Okay, uh, this we have studied. And if you can recall the formula of slew rate, SR. SR was given as variation in the output voltage with the variation in time, delta V naught upon delta T. Okay, so uh, from this relation, what we can find? We can find the variation in output voltage V naught will be equals to voltage gain multiplied by input voltage. So I want to calculate the value of variation in V naught with certain variation in time, that is delta V naught upon delta T with the value AVD times variation in delta V in with the value delta T. Or effectively from this relation, from this relation, what we can understand, that is my voltage gain AVD will be equals to this quantity divided by this quantity. That means delta V naught upon delta T whole divided by delta V in divided by delta T. So now we have just variate the formula, and if you can see, if you can just do the comparison, this numerator component is my SR, slew rate, and this denominator part is given in the problem. So I can easily calculate the value of AVT. It will be equals to slew rate, and slew rate is given 2 volts per microsecond divided by variation in, that is delta V in. So it is given as 0.5 volt, 0.5 volts divided by delta T. In how much time? 10 microseconds. In 10 microseconds. So ultimately it will be 2 multiplied by 10 divided by, so volts per microsecond will be cancelled out, divided by 0.5. So my closed loop voltage gain AVD should be equals to 2 multiplied by 10 multiplied by 10 divided by 5. So 5 is cancelled by 2, and AVD with this data is 40. So this is very interesting numerical. The value of differential gain should be 40 in order to meet out this relation. Problem number 5. Calculate CMRR for the for the measurements given in following circuits. Given circuit diagram. So here output voltage, Input voltages are given. This is V in 1, and this voltage is given as 0.5 volt to non-inverting terminal. Inverting terminal V in 2. This is given as minus zero point 0.5 millivolt. So in fact, this is also given in millivolts. So both values are given in millivolts, and output voltage received with this measurement is 8 volt. So output voltage from this is 8 volt, and the second measurements are the two inputs V in 1 is given as 1 millivolt, V in 2 is also given as 1 millivolt, and in this case output voltage V0 is given as 12 millivolt. So these are the situations given, figure 1, and this is my figure 2. So in figure 1 you can check similar but opposite polarity input is applied. Okay, similar but opposite polarity. So it is similar but opposite polarity signal is applied. So in this case, if you can recall with the previous discussion, or explicitly I can write the term difference voltage Vd equals to V in 1 minus V in 2. So by doing this, I will have Vd will be equals to 0.5 millivolt minus 0.5 millivolt, it is 1 millivolt. And in the same situation, the common mode signal Vc will be equals to 1 by 2 V in 1 plus V in 2. So for scenario number 1, you can check Vc will be equals to 0 volts. And in second case, you can check same in magnitude as well as in polarity. Okay, so same polarity signal, same polarity signal is used. Same polarity signal is used. So with the same exercise now, Vd will be equals to 0 volts. And what about Vc? The common signal is 1 plus 1 2 divided by 2 is 1. So it is 1 millivolts. So from this analysis, you can check my V naught will be equals to simply A D, that is differential voltage gain. And from this analysis, what we can understand, my V naught will be equals to ACM, that is common mode rejection. Okay, so I can draw the circuit diagram so that one can easily understand the term. Now I am having a differential input over here Vd, and the value of Vd is 1 millivolt I have applied, and receiving V naught equals to 8 volt. So if I am receiving V naught equals to 8 volt corresponding to 1 millivolt, that means in this situation, what is the value of differential gain? 8D equals to output upon input. So it is 8 divided by 1 into 10 raised to power minus 3. That means the value of differential gain AD will be equals to simply 8000. This is the value of AD. And value of common mode signal is over here. So it was 12 millivolt output we have received over here. So now I am drawing the circuit of this also, so that one can easily understand the output. So both are short circuited, and a common signal is given. The value of common signal we have just calculated, 1 millivolt. So this is 1 millivolt, and output which we have received is 12 millivolt. So you can check my ACM will be equals to output upon input, 12 millivolt divided by 1 millivolt. That means my ACM equals to simply 12. If you can recall now the formula of CMRR, so my CMRR equals to AD upon ACM. I am having the measurements. AD is 8000, ACM is 12. So by solving this, I am having the result 666.7. This is the value of CMRR. In fact, you can also solve in decibel. I am having the results. I am directly sharing CMRR in dB. So it will be equals to 20 log of base 10, 666.7, which will be equal to 56.4, 56.48 dB. So these are the results. So I'm stopping the discussion. Thank you.